Welcome everyone. Today we have a lunch talk given by Professor Fernando Metz. Fernando works in University Rio Grande do Sul in Brazil, and he works on different problems in complex systems and in statistical physics. And what's special about his work in general is that he always applies this lens of random matrices to study different questions. And random matrices is also a topic of his work today. Please, you're very welcome. The floor is yours.
Okay, so thank you very much, Ivan, for the nice introduction. And I would also like to thank the center for the invitation. It is it's very nice to attend this gastronomic and scientific event. And well, before starting, I want to thank also my collaborator in this work, Isaac Neri from King's College in London, with whom all results that I will present to you have been developed in the last few years. And well, I changed a bit the title, so my talk is going to be, I want to talk about random matrix theory and complex networks. And well, the colloquium is divided in two main parts. So in the first part, I will give you an overview of random matrix theory. This will be very basic. So I will talk about motivations and why random matrices are interesting tools to model large complex systems. I want to give also a flavor of my own work in the field. And then in the second part, things will become a bit more technical. Then I will show you a few analytic results that we have derived for the particular case of complex networks with directed interactions. Okay, because I think that these results might be somehow interesting or maybe even useful for your own work. Okay, so I start with a few examples of complex systems in different areas. We have complex systems in nuclear physics, in which we have, for instance, large heavy nuclear with lots of particles interacting in a very complicated way with each other. We have very important examples in biology, such as food webs or ecosystems and neural networks. Examples in technology, the www network is a classic example. And also finance and economy. Here I show the daily stock market prices of different countries. As you can see, there are some correlations here, which somehow reflect the interactions between the markets of the different countries. And finally, I show also an example of a social system. And this is a corruption network extracted from data in Brazil. And if two individuals here engage in a corruption scheme, we put a link between them. Okay, so as you can see, the network is very well structured and pretty large, which is not really surprising, at least for me. So what all these systems have in common is that in general, we have a large number of elements that interact in a very complex or complicated way, and the interactions are somehow difficult to measure or to predict. There are many questions, of course, that one can ask about these systems, and a very important set of questions concern how this pattern of interactions influence dynamical processes that take place on the system. And the simplest way to approach this problem is through a linear dynamics of this form that I show here. So X is a vector that encodes the degrees of freedom, M is a matrix that couples the variables X, and the physical meaning of these quantities depends on the system under study. Here I show three different examples where this type of description is quite important. And well, we can solve this linear dynamics for X in terms of eigenvalues and eigenvectors of M. And it turns out that the spectral properties of the matrix M intermediate the relationship between the interactions and the dynamics. Okay, so it is very important to understand the spectral properties of the matrix that controls the interactions in large complex systems. So how can we model the matrix M? So this is where random matrix theory enters into the game. So random matrices were popularized in the 50s in the field of nuclear physics. And well, during that time, people were interested in heavy nuclei, such as uranium, that contains more than 200 particles. And the problem is that one cannot write down the full Hamiltonian for such a system, but we do have access to experimental data. So here I show the experimental energy levels of uranium. And as you can see, the sequence of levels looks pretty random. And Eugene Wigner looked at this data and said, well, maybe we should try to model a large Hamiltonian by replacing by a random matrix. For instance, a matrix drawn from a certain distribution, a Gaussian distribution, which would be the simplest choice. Of course, there are physical constraints here, but it turns out that with this very simple approach, Wigner was able to reproduce some experimental data. And here I show a very simple example. This is what is known as the level spacing distribution. This quantity is just a histogram of the separation between consecutive energy levels. So the smooth curve here is the result from the random matrix approach, from the theory. And the other curve here is a histogram obtained from experimental data coming from different chemical elements. Okay, so in this way, random matrix theory became popular. And what I call here the Wigner-Dyson approach consists in replacing the complex interactions in a large system by a random matrix ensemble. And there are essentially two motivations for doing that. The first one is that we do expect some sort of universality in the sense that certain statistical properties that we measure related to the behavior of our system should be rather independent of the details of the interactions. And second, the interactions are in general difficult to measure or difficult to predict in large complex systems. So these are essentially the two motivations. And okay, so Wigner came with the first ideas, but Dyson put forward the philosophy of this approach. And I think that this sentence of Dyson that I picked up from one of his classic papers in the 60s captures very well the spirit of this approach to model large complex systems. So this idea spread to different fields. In 1972, Robert May wrote his very famous paper in theoretical ecology, in which he uses essentially the same approach. So he replaces the interactions of a large ecosystem by a random matrix. And more recently, Morin and Jean-Philippe Bouchot, again, follow the same procedure to model the interactions in a large economy. Well, Jean-Philippe Bouchot is going to talk exactly about this type of problem next week here at the colloquium. Okay, so good. So in the random matrices, we deal with the eigenvectors and eigenvalues of a matrix A, in which A is composed by random entries. And it is very simple to state the central aim of the theory. So given a joint distribution of the matrix elements, we want to learn something about the statistics of the eigenvalues and eigenvectors when the dimension of the matrix becomes infinitely large. So there are several things that one can compute about the spectral properties. So here I show some examples of observables. And the most famous and most well-studied family of ensembles in the theory is the so-called Gaussian ensembles. So in the case where the matrix elements are real valued, it is very simple. You simply draw the elements they are identically and they are independent distributed random variables drawn from a common Gaussian, okay, which has some mean and variance. Okay, so why is this interesting? To answer this question, I quote Alan Edelman, who is an important mathematician in the field of random matrices and in other areas, I suppose. And he says that if you take any important mathematics, such as linear algebra, and you randomize, this will have many applications. Okay? So this is, in fact, true. Random matrix theory finds plenty of applications in different fields. I mentioned already 3. Theoretical ecology, nuclear physics, and economy. There are also applications in number theory, quantum chaos, neural networks, complex networks, Anderson localization, and so on and so forth. Okay, and one of the reasons why random matrices have such large number of applications is because some spectral observables exhibit universality. So let's have a look on that in the simplest case of the spectral density. So this quantity here simply gives the density of eigenvalues in the neighborhood of a certain point, lambda. Lambda may be complex or real, depending on the nature, on the symmetry of the matrix. And well, I did here a very simple exercise. So I generated a symmetric matrix with Gaussian distributed elements with this distribution here. I computed the eigenvalues and then I did a histogram. This is the outcome shown in as a red curve. As you can see, there are some small fluctuations here, but apart from that, the shape of the curve is very regular. And it turns out that we can compute the functional form of this curve when n goes to infinity. And one can show that the shape is given by this function here. This is called the Wigner law for symmetric Gaussian random matrices. Okay? If we now drop the symmetry constraint and we repeat the same numerical experiment, we see that the eigenvalues now spread in the complex plane, but again, the density here looks uniform, and in fact, we can once more compute the spectral density for this class of models when n goes to infinity, and we can show that the density is uniform inside a disk of radius 1. This is what we know as the circular law for asymmetric Gaussian random matrices. Okay, so these results hold here for Gaussian, for the family of Gaussian ensembles, but it turns out that this is more general. One can show that these two eigenvalue distributions, they hold for any distribution of individual elements of the matrix, provided the first two moments of the distribution are finite. And this is what I call here universality. This is completely analogous to the central limit theorem in probability. And universality in the case of asymmetric random matrices was proven by Terence Tao and Van Wu in 2008. And this is, at least I find this quite a recent result, given that this type of ensembles were introduced in the 60s. Okay, so have a question?
No constraints on higher moments?
Well, as far as I know, no. You need to have the first two moments. Maybe the fourth moment has to respect some bound, but apart from that, it is extremely general, this result. Okay, good. So we have a very good control of this type of ensembles. And however, as we have seen in the first slide, we cannot model all types of systems using Gaussian random matrices. So we have to introduce more sophisticated tools to deal with systems that are somehow organized in networks. And these tools are graphs or networks. And informally speaking, a graph is a collection of nodes interconnected by edges or links. And here I show a very simple example of a graph with 4 nodes. This is the adjacence matrix, which encodes the interactions in the graph. So for instance, if there is a directed link going from node 1 to node 2, we put the element A12 equal to 1. If the link is absent, we put 0. Okay? If there is an undirected edge, which has no preferential direction, we have elements in the matrix that are symmetrically placed. That corresponds to a symmetric position in the matrix. And well, we can also introduce certain tools to study the structure of the graph. And the primary tools are the degrees. We can define the in degree of a certain node I, and this is a variable that simply counts the number of directed edges that point to I. And we can also introduce an out degree, which is the number of edges that leave us at the node I. If the network is undirected, such that all links are undirected, then the in degrees are obviously equal to the out degrees. Okay, this is a very basic set of tools. We can now go to the more real-world examples, such as this food web and its corresponding adjacence matrix. And we can once more now use the Wigner-Dyson approach and try to model this type of system with an ensemble of adjacence matrices. Okay, so that's the idea. We introduce an ensemble of adjacent matrices, what they call here also a random graph model or an ensemble of random graphs. So there are several ingredients here that we can put in your model. The matrix can be asymmetric, symmetric. We can have weights at the different edges. But here there is an important distinction that I want to highlight, which is between dense and sparse networks. So in the case of dense networks, the average number of links is proportional to n squared. So essentially, one point of the graph interacts with all others, while in the case of sparse networks, the average number of links grows linearly with the system size. So one point interacts with a finite number of others. Okay, this distinction is very important. as you probably noticed, Gaussian random matrix theory applied to dense networks. Okay, so if we want to understand this type of problem, this type of system here, we need to deal with sparse random matrix ensembles, in which the adjacency matrix has many zeros. Okay, so let me show you the spectral density for a very simple model of undirected networks, which is the Erdős-Rényi random graph model, popularized by Paul Erdős and Alfred Rényi. Here I show this very famous picture of Paul discussing mathematics with Terence Tao at the age of 10. And the model is very simple to define. We simply draw the elements of the matrix according to this probability distribution. Okay, so we put 1 at a certain position of the matrix with probability C over n, and we put 0 with this probability here. This is how we generate the adjacent matrix in this case, and the sparseness of the model appears in this parameter C. So if we keep C of order 1 while we send n to infinity, the resulting graph will be sparse. Okay, so it turns out that C is the mean degree of the graph, and we can also compute the degree distribution in this case. If C is finite while n goes to infinity, the degree distribution has this Poisson form. Okay, so I did the same exercise as before. So I computed the eigenvalues for this type of model, and then I did a histogram, and this is the outcome for the spectral density for 2 different values of C. So the first thing we notice is that the spectral density is not given by the Wigner law, so the universality is broken for this type of system. And second, there are 2 properties here that I want to highlight. The first one is the existence of these spikes in the spectral density, and the spikes, they appear because now the graph can have a very giant, strongly connected cluster and many finite clusters separated from this percolated giant component, and the eigenvalues of these finite clusters, they accumulate at certain specific points of the spectrum. So these are the eigenvalues of the finite cluster, mostly, okay? There are different contributions that can enter here in the delta peaks. And the second property is the existence of tails in the spectral density. Actually, the spectral density now is supported on the entire real line, and the shape of the tail here is usually related to the shape of the degree distribution. So these are 2 different properties that are completely absent in the case of Gaussian random matrices, and which reflect somehow how the structure of the graph impacts the spectral properties. Okay, so my research has been concentrated on sparse random matrix ensembles. So one of the things that I've been doing is to try to come up with new analytic techniques to deal with this type of random matrix ensembles, for the simple reason that most of the analytic methods were developed for Gaussian random matrices. So they apply only to describe dense random networks, okay? And most of these techniques, they come from a combination of statistical mechanics and spin glass methods, such as cavity method and replica method. And these are the type of things that we have been trying to do in the case of sparse matrices, that we can use these results for complex networks. So the questions here are concern the role of the structure of the graph and the spectral properties. This is a very important question. And secondly, we would like to understand whether this type of ensemble exhibits some universal properties. Okay, so this is just to give you an idea of my research. So now, in the rest of the talk, I will focus and I will present to you a few results for sparse and directed complex networks. These are analytic results that connect the structure of the graph with the spectral properties. And well, directed networks are important because you can model certain real-world complex systems, such as the WWW network, neural networks ecosystems. These are classic examples that have many directed links. And we would like to study a model in which we can control, for instance, the degree distribution, see how it impacts on the spectral properties. And the model that is suitable to that is the configuration model. And this is a bit more sophisticated than the Erdős-Rényi random graph model. And well, we generate a single instance of the model as follows. So we fix the total number of nodes, and then at each node we draw the in degree and the out degree from a common probability distribution P of k with average C, and we draw these in degrees and out degrees at the different points independently. Okay, so we simply draw these numbers. So we have a prescribed degree sequence. We have to impose that the total number of edges leaving the nodes is equal to the total number of edges entering the nodes. And then after we have our degree sequence, we can now choose at random a pair of nodes and then connect them with a directed edge. So we repeat this procedure a large number of times, which of course depends on the size of the graph, until there are no edges left. Okay? In this way, we will have an instance of the graph with a prescribed degree sequence that we can control because we control the degree distribution. Of course, when we do this iteration procedure, we can have self-connections and also multiple connections between nodes. But the number of these events is just finite when the graph becomes very large. So we just do some rewiring because we don't expect this will affect much the spectral properties in the limit of n going infinite. Okay? Good. So after we have generated a single instance of the graph, this is how the graph looks like. We have only directed the edges between different nodes, and we can simply read the adjacency matrix. We also assign weights to the different couplings in the graph. So Jij here is the string of the coupling that goes from node I to node j, and we draw these numbers from a certain distribution P of j. So the model is fully controlled. The ensemble of graphs is fully controlled by only two distributions: the distribution of the couplings and the degree distribution. Okay. So let us have a look on the eigenvalues of this model, and here I show the eigenvalues of 5 realizations of the configuration model with a Poisson degree distribution. So first we see that there is a large concentration of eigenvalues inside this black circle here, and this is what we call the bulk of the spectrum, because when n goes to infinity, this part here will develop a continuous or an absolute continuous part. This is where the absolute continuous spectrum will appear. Outside the bulk, we have what we call an outlier or an isolated eigenvalue separated from the bulk by a gap. And we have also the boundary of the bulk, which we will define as lambda p. Okay, so just a technical remark for those that are familiar with percolation in directed random graphs. All results that I will discuss here hold for C larger than 1, because only in this particular regime that the graph has a giant strongly connected component, because we need to have this component such that the spectrum has a continuous path. Okay? Good. So I want to show you some analytic results for the average position of the outlier, for the radius of the boundary, and for the eigenvectors along the boundary of the bulk. And I will show you analytic expressions that connect these quantities with the structure of the graph. Why am I interested in this particular part of the spectrum? Because if we order the eigenvalues according to the real parts, for instance, the eigenvalue with the largest real part is the leading eigenvalue. The corresponding eigenvector is also called the leading or principal eigenvector. And among all eigenvalues and eigenvectors, the leading eigenpair is the most important one for applications. So here I show you a list of important applications of the leading eigenpair in dynamical processes, phase transitions, and algorithms. Of course, I don't have time to go into the details here, and I also don't have the background to go into all the details. But the important point is just to give you a convincing list that the leading eigenpair is very important for application. Okay. Good. So before showing you the main results, I just want to give you an idea of the method, at least an argument of why this type of models is solvable. And the main property is that renders the model solvable is the so-called local tree-like structure. This means that if we generate a very large graph from the model, then we zoom around a certain node I, we pick up at random a node and we look how the neighborhood looks like. The neighborhood is arranged in a tree. So the probability of finding a short loop in the neighborhood of I goes to 0 when the graph becomes infinitely large. And it turns out that if we remove now this central node I from the graph, we get what is called the cavity graph. There is a hole now in the graph. And if we have certain dynamical properties defined on the different nodes, for instance, suppose you are studying the easy model and you are looking at the local magnetizations, the local magnetizations here will become independent. Because a path going from this point to this point contains a number of edges that is proportional to the logarithm of the system size. So the model does have loops, but the loops are very long. Okay, so that's the main property. So what we usually do, we compute dynamical variables on the cavity graph because these guys here are independent, and then we reconstruct the dynamical variable at the central node from some sort of recursive scheme on the tree. Okay, so that's just to give you an idea, and the main outcome of this calculation, this is called the cavity method. There are also other names such as message passing or belief propagation in computer science. So if we apply this method, we can get a very simple equation for the eigenvector components. So this equation applies only to the case of directed graphs with a local tree-like structure. Okay, and this is a very simple expression, and Z here lies outside the bulk. Partial I out here is the out neighborhood of a certain node. And this is just a linear equation for the eigenvector components. This is, of course, I cannot give you, I don't have time to justify this, but this comes out of applying the cavity method. Okay, and a very nice property of this equation that again comes out of the calculation is that all random variables here are statistically independent. So, for instance, Jij is independent of the eigenvector components, and this means that I can simply now take ensemble averages on both sides of this equation and get fixed point equations for the moments, for the first moment, for the second moment of the eigenvector components, and then we can try to solve these fixed point equations. And that's what we did, and all results that I will discuss now come from this simple equation and from the equations for the moments. So if we look for the equations for the first and second moment of the eigenvector components, we find that the first moment is different from zero if that parameter Z, which is a free parameter, lies on the top of the outlier. So the outlier is simply given by C times the first moment of the coupling strengths. And the outlier appears in the spectrum only if this condition is fulfilled, which means that there is a competition between the mean degree and the fluctuations of the couplings. So we will see an outlier only if the mean degree is large enough in comparison to the fluctuations, which are controlled here by the ratio between the second moment and the first moment.
And the Z is the eigenvalue.
Z is a parameter in the complex plane outside the bulk. So we want to find a solution for the equation for the moments. And you find that this equation has a non-trivial solution only when Z lies on a certain specific point of the complex plane, which is the outlier.
Right.
So that's the logic.
And then you connected that eigenvector to that specific...
Yes, then you can compute also the eigenvector on the top of that specific point that you found a non-trivial solution. A non-trivial solution here means normalizing. So if you take any other point in the complex plane, the solution, because it is a linear equation, so it just diverges or it goes to zero.
Right.
So you have non-trivial solution only if Z lies on the top of an eigenvalue. So if you look for solutions in which the first moment is zero and the second moment is different from zero, you find that Z now lies on the top of the boundary. So the radius of the boundary depends on Z and on the second moment of the distribution of the couplings. So these are two very simple expressions that connect the spectral properties with the structure of the graph. So let me show you how this compares with numerical experiments. So here we show the leading eigenvalue as a function of y for different models. Y here is the parameter that controls the ratio between the fluctuations in the couplings and C. And the different points here are for different degree distributions and different distributions of the couplings. So we just diagonalize the matrix, find the leading eigenvalue, and rescale by this factor. So we see that when we rescale the leading eigenvalue by this factor, the data collapses on the top of the solid line, which is our theoretical result. And, well, this means that the leading eigenvalue is a universal function of y in the very precise sense that it depends only on a few parameters that characterize the network structure. Okay, so we see that for y sufficiently small, the spectrum has a gap because the leading eigenvalue is given by the outlier. As we increase y, the gap closes in a continuous way, and we have what we call here the gapless transition. Okay, so this is the main result about the eigenvalues that I want to show. It's
the degree distribution is not involved.
Sorry?
The degree distribution is not involved.
No.
Yeah.
This is for two different degree distributions, Poisson and regular. We have also results for other degree distributions.
Yeah.
So if you just compute the linear eigenvalue, we scale by that factor, you get everything collapses on the same.
Yeah.
On the same.
Yeah. And C is average degree. Or
C is the average degree.
Because that's the only link to the.
Yeah. Sure. But I mean, it depends only on a few. It depends only on the average degree, right? Yeah. So that's the. There are different concepts of universality, right? Yeah. And we claim here that universality means, in this sense, that it doesn't depend much on the degree distribution and the distribution of the coupling. So that's the claim. Okay, so let me now shift to eigenvectors. I want to discuss something about eigenvectors. And generally speaking, eigenvectors are interesting because they undergo, well, among other reasons, they are interesting because they undergo a localization transition as a function of the disorder or the randomness in the complex system. So if the randomness is absent or very small, the eigenvectors are extended. So the number of non-zero components in an eigenvector, which are called here V, is proportional to the system size. So if the disorder is sufficiently strong, the eigenvector localizes in a few degrees of freedom. Okay, so the number of non-zero components remains finite when we set the size of the system to infinity. And well, this transition appeared in the 50s in the condensed matter. Very important paper of Phil Anderson. And soon people realized that this was important for several different fields, and it is actually also very important for complex networks. And you can see some applications of this transition for complex networks in that list that I presented in the previous slide. I just want to give you one concrete example, which is in the context of epidemic spreading. So if you look to a very simple model of epidemic spreading, such as the SIS model, we know that above the epidemic threshold, so increase the infection rate, and above the epidemic threshold, an extensive number of individuals get infected, right? So this is the normal scenario. But now if you look right above the threshold, one can show that the number of infected individuals is related to the leading eigenvector of the adjacency matrix. And it turns out that if this eigenvector is localized, the epidemic does not spread, even though we are above the threshold, right? So the point I want to make here is that this qualitative change in the eigenvectors usually has consequences to dynamical processes on networks. Okay, so in the case of undirected networks, the leading eigenvector has been studied, and here I show the components of the leading eigenvector for a regular graph in which all nodes have the same degree. So you see that the components have all the same value, approximately. And if you now move to a graph in which the degrees follow a power law distribution, the eigenvector becomes localized on a few hubs of the network. So the idea is that degree fluctuations here are essential to the essential mechanism to localize the eigenvectors. The leading eigenvector, I'm talking about the leading eigenvector of undirected networks. So let us see what we can learn about directed networks from our equations. To study localization, we computed a parameter called the inverse participation ratio, defined according to this expression. And this quantity here, one can argue that it is proportional to 1 over the number V of nodes participating in an eigenvector. So if V scales with the system size, if it is proportional to the system size, the IPR remains finite when n goes to infinity and we are in an extended phase. So if V remains finite, when we take n going to infinity, the IPR diverges and we are in a localized phase. So this is a very nice parameter that distinguishes between localized and extended eigenvectors. We did not invent this parameter. This is known for 70 years probably, or maybe a bit less. Okay, so we computed this quantity for directed random networks, and this is the main outcome for eigenvalues along the boundary of the bulk. Okay, so this is again a very simple formula that connects the structural properties of the graph with the IPR along the boundary. We have an analogous formula for the IPR corresponding to the outlier eigenvalue, but it is quite long, so I decided not to show. But all results that I will show you here, they apply in an analogous way to the outlier. So what can we conclude now from this formula? First, that if the second moment of the degree distribution diverges, then the eigenvectors along the boundary of the continuous spectrum will be localized. So this is the same mechanism that we have seen before in the case of undirected vectors. We see that there is another possibility here because the denominator of this expression can go to 0. So let us see how the IPR behaves as a function of the mean degree C. So this is a plot of the IPR as a function of C. The points are numerical results obtained from the solution of the eigenvector equations, and the different lines are the theoretical expression for different degree distributions. So I took here 3 different degree distributions. I show here the tails of these distributions. The important property is that all moments of each degree distribution, they are just finite, okay? Because I don't want to see any influence of divergent moments. As you can see, the IPR here diverges at a common critical point, which is independent of the degree distribution, and we can compute this point here, okay? So the critical point depends only on the fluctuations of the couplings, and this was quite surprising to us because, in general, critical points do depend somehow on the details of the interactions in your system. Critical points are, in general, not universal quantities. So, and the main conclusion here is that there is an additional mechanism for localization. Localization can be induced by fluctuations in the weights, in the couplings, the strength of the couplings. Okay, so to finish, I just want to show you a very straightforward application of these results to the stability of large complex systems. So there are some systems that can be described by a set of differential equations of this form. Fi here is a nonlinear function that couples the different dynamical variables. This is very important to describe, for instance, neural networks and ecosystems. I will use here the language or the terminology of ecosystems to discuss these results. So in this terminology, Xi is the abundance or the density of species I. And well, what I want to discuss here is the response of these systems to external global shocks. Okay, so suppose that you have an external perturbation that changes a little bit the abundance of all the species. This could be, I don't know, it could be pollution, it could be global warming, and well, we want to see what happens if the system lies in a fixed point, such that all abundances are stationary, and then we perturb a little bit the behavior around the fixed point. So we can now expand the right-hand side and derive a set of linear differential equations for the perturbations ui. So ui here is just the deviation of the abundance of species I with respect to its equilibrium value. And here we have introduced by hand a parameter called self-regulation, because we want the system to be stable if it does not, if the species do not interact. So if we do not have interactions, the perturbations just relax exponentially to 0. Okay, and the system will be stable. The question here is precisely what happens when we switch on the interactions between the species. And the interactions are controlled by the community matrix, which is just the Jacobian of the function f, comes out from the linearization. So this element here just tells us how a change in the abundance of species J affects the growth rate of species I, right? Okay, so now we can solve this linear system and show that the system will be stable, which means that all perturbations will go exponentially to 0, provided the real part of the leading eigenvalue is smaller than the self-regulation. So that's the condition for having a stable system. Okay, so now I will draw my matrix from the configuration model of directed graphs, and I will use the results that we have derived before to study the stability of this type of system. So the question here is, what are the ingredients that promote stability, right? So Before showing the results for directed networks, I just want to review previous results. So in the case where the community matrix is drawn from a Gaussian distribution, the real part of the leading eigenvalue is proportional to square root of n, and the system is always unstable when n goes to infinity. This is one of the main conclusions of Robert May in his important paper of 72. If we now move to sparse and undirected networks drawn from the configuration model, one can show that the expected value of the largest of the leading eigenvalue scales like square root of the maximum degree. And this implies that the stability is now controlled by the degree distribution. So when n goes to infinity, if the degree distribution is unbounded, the system will be unstable. And finally, in the case of sparse and directed networks drawn from the configuration model, the real part of the leading eigenvalue, according to our results, is of order C or square root of C, depending if you are talking about an outlier or an eigenvalue at the boundary, and the stability is only controlled by the average degree. So we can have a stable system even if the degree distribution is unbounded, in the case of directed networks. So the main conclusion here is that directed networks are in general more stable than their undirected counterparts. And the intuitive argument behind that is that undirected networks contain many feedback loops. So for instance, if we perturb here the abundance of a certain node, this perturbation propagates to a neighbor, and then after some time, because the interactions are undirected, the perturbation somehow, the effect of the perturbation returns to the initial node and somehow amplifies the effect of the perturbation. So these feedback loops, they make the stability in undirected networks very sensitive to high degrees in the network. In the case of directed networks, we do not have feedback loops because the network is locally tree-like and the links are all directed. So if you perturb a certain node, somehow the perturbation does not, it's just spread in the system, does not, you do not have feedback loops. So that's the main argument. So stability in directed networks, again, does not depend much on the degree distribution and on the distribution of couplings. It depends only on these three parameters here. And I show here the stability diagram of C versus alpha. Alpha controls the fluctuations in the coupling strengths. So below these solid curves here, the system will be stable. Each solid curve was generated for a single value of the mean value of the coupling strengths. And we see that there are two different qualitative regimes here. So if we are on the right of this dashed curve, then the stability is controlled by the bulk. And as we increase the fluctuations in the couplings, the value of CGs decreases, the system becomes less and less stable. So if we are to the left of this dashed curve, stability is controlled by the outlier, which is insensitive to an increase in the fluctuations of the couplings. So if we increase alpha here, the value of C remains constant, and the system in this part of the stability diagram is more robust to fluctuations in the couplings. Okay, so the conclusion is that the spectral gap is beneficial for the stability of systems of this type. Okay, so this is all that I wanted to discuss. This is just a summary of the results. I talked already too much. I just want to say that we are now comparing these expressions with data from empirical networks. And the idea is actually to come up with a minimum model, try to understand what are the minimum ingredients that we have to put in the model to reproduce the behavior of the leading eigenpair of directed networks. Okay, thank you.